Question 1, it says a nucleus of the isotope radium-226. Now this 226 is the atomic mass number. It's the number of protons and neutrons of the atom. And it says it undergoes alpha decay with a half-life of 1.6 times 10 to the 3 years to form radon, Rn. Now define in terms of isotope and half-life. Sorry, define the terms isotope and half-life. So isotope, okay, so an isotope is a nucleus or an atom, nuclei, which have the same number of protons but different number of neutrons. So they're the same element, but they've got different number of neutrons. So they've got the same number of positive charges, therefore the same number of electrons in the neutral state, but they've got different number of neutrons. So the mass of the nucleus is different. And then the half-life, to define this. Now this is the time taken. The time taken for the activity of a radioactive sample to decrease to half. That's one way of doing it. So you're looking at the time taken for the activity of the radioactive sample to decrease to half its original value. You can also, it's viewed in terms of the number of radioactive nuclei. It's a time taken for the number of radioactive nuclei in a sample to decrease by a half. Question B, it says, using the grid below, sketch a graph to show how the activity A of a sample of radium-226 Ra would be expected to vary with time over a period of 5 times 10 to the 3 years, 5,000 years. The activity of the sample at time t is equal to 0 is A0. So this is our starting off. Now we know that this is going to, every half-life, it's going to half. So let's put in these half-lives. We are told that the half-life of this is 1.6 times 10 to the 3 years. So looking at our time scale, this is 10 to the 3. So this would be 1.6 over there. And then we'd get 3.2 over there. And then we'd get 4.8 over there. So we'd get something like that. Now we've got to make sure that this is our half-life, the amount. So we've got 1, 2, 3, 4, 5, 6, 7, 8. So obviously we're going to start, our first half-life will be at 4. 2, 3, 4. So we would be over there. Sorry, my board's not totally. Then it would be go to 4. So that would be A0 over 2. And then the next one over here would be A0 over 4. That would be over here. There. And then it would be A0 over 8. It would be half again. So it would be down over here, and that would be over there. So to get those points. So those are our points. Now we've got to draw a smooth curve. Now, so we'd have to draw a smooth curve through all of those points. So we'd get a graph something like that. Here it says the nuclear reaction equation for the decay of radium-226 may be written as this. So we've got our proton number. We've got our proton number is equal to 86. There, this is 80. It's let me write this a bit bigger. 88. Sorry, 226. So, sorry for a moment. So let's just look at what's going to happen there. So we're going to get your RA, which is 88226, and that goes to Rn plus your alpha particle. Now your alpha particle is 2 and 4, so we need to balance these out. So this over here is 88, this is going to go to 86, and here you've got 4, so this is going to be 222, because you want these to balance. So you want the 222 plus the 4 to equal your 226, and your 86 plus your 2, adding those two to equal 88. It is important that you know what an alpha particle is. That's standard knowledge that you need to know. So we're going to get this is 86. Now here we are looking at your neutron number. So it's 222 minus 86. And obviously that is 130 to 136 would be that value. So I'll outline why the binding energy of Ra is less than that of Rn. So what's happening here is that this is your radioactive substance. So this is unstable, and this becomes more stable, and therefore your binding energy has increased. So in the radioactive process, you're getting a stabilization of the nucleus. Therefore your binding energy is increasing. This alpha particle, by being emitted from the nucleus, is taking away energy in the form of kinetic energy, and so it is leaving a more stable daughter nucleus behind. Okay, I think you'll be able to get for your 2 marks there. You should be able to get that. Then it says the following data are available. You have got the mass of the Ra is 226, and you've got the mass of the Rn is that, and the mass of the alpha particle is that. Now show that the energy release in the decay is for the nucleus is this. Now what we just got to do is basically we just got to do simple subtraction. So we got to just take that and we've got to subtract from that 0.0175 plus, and also still in brackets, 4.0026. We've got to subtract that, and we're going to get our value in terms of atomic mass units. So let me just do that. So we're going to get 226.0254 minus brackets 222.0175 plus 4.0026, and I get, in terms of U, I get 0.0053 U. So that's this over here. Now each 1 U corresponds to that. So I've got to multiply this 0.53 times 931.5, and I get, therefore it equals 4.94 mega EV when I do it on my calculator there.